Hi kids, I don't have a lame joke for you. Guess you have to come up with your own lame joke. Maybe you can get one from mom or dad or from your brother or your sister, and you can bring it in class and share it with us. We're going to go ahead with section 7.4, which is solving systems of equations by the substitution method. Now, if you've checked your email recently, you'll notice that I sent you a link to a video teaching from section 7.2, which is one that I did last year where we're talking about dependent and independent solutions, systems of equations, and consistent and inconsistent systems. You will definitely want to go back and look at that video, or you'll want to make certain that you have studied the teaching in your text from section 7.2. There's vocabulary here that is essential that you understand. Basically, if you have a system of equations that is consistent, that means that you have an answer to it. There is at least one solution. Remember that we have the three ways in which our lines can interact with one another. One line can be right on top of another, they can cross at one point, or they can be parallel to one another. So if then a system of equations is consistent, it has at least one solution. It might have an infinite number, but it has at least one. If it has an infinite number of solutions, which is this, then it is both consistent, meaning that it has a solution, and dependent, which means that it has an infinite number of solutions. If it is consistent, having a solution, and independent, it has one solution. If it is inconsistent, that means that there are no solutions and it's parallel. And you can look at two equations that have been graphed, and you can say, okay, this right here is an inconsistent pair of equations because the lines never cross. This is consistent independent because it has one solution. This is consistent dependent because there are an infinite number of solutions. But how do you tell how to categorize those equations if you don't see them? Well, that's what we're going to learn today in this chapter. We're going to learn how to categorize systems of equations as consistent or inconsistent based on something algebraically. So let's go ahead and begin with example on page 284 of Bob Jones University Press, Algebra 1, page 284. The first example here that's not even illustrated, not even given as an example, we have x plus y is 5, and then we have x plus y is 7. Let's go ahead and solve this system of equations by substitution. I'm going to take my first equation over here and solve for y. And I have negative x plus 5 being the value that we end up with for y. I've solved for y. Let's take negative x plus 5, substitute it into this equation and see what we get. I have negative x, substituted in for y. Not going to do me any good substituting it in for x because that would be completely incorrect. I have x plus negative x plus 5 is equal to 7. X plus the opposite of x, it goes away. I end up with 5 is equal to 7. And I don't know about y'all out there in TV land, but the land that I live in, 5 is not equal to 7. So I have ended up with something that is not true. What does that mean? Well, what that means is that you have two equations here that are inconsistent, meaning that there is no solution to them. So if there's no solution, according to the definitions that we've had, those lines have to be parallel, right? Well, let's see what happens if we sketch this. Let me see how far down I can go. Sketch these two graphs. what do I have? Y is equal to negative x plus 5. And then I have y is equal to negative x plus 7. Okay, 1, 2, 3, 4, 5, 6, 7. The y-intercept is 7. The slope is a negative 1, dot, dot. And this is approximately the graph of the line y is equal to negative x plus 5. Now, I'm sorry, negative x plus 7. Now, same thing. Slope is negative 1 over 1. And this right here is approximately the graph y is equal to negative x plus 5. What you see that we have here bears out what we said. There's no solution. These lines, if they were drawn correctly on gridded paper, would be very clearly parallel. And if you look at the slope-intercept form of these lines, you've learned that lines that have the same slope are parallel to one another. They just have a different y-intercept. So, algebraically, when you are solving a system of equations, if you come up with a statement that is false, 5 is clearly not equal to 7, come up with a statement that is false, this means that you have an inconsistent system of equations, which means that you have a set of parallel lines. Now, moving on, let's see. The next thing that we want to talk about, we have x plus y is equal to 2, 3x plus 3y is equal to 2. This system of equations right here has a solution. Means that it's consistent, but it has an infinite number of solutions, meaning that it is dependent. Well, how can I tell that this is an independent system of equations? I'm sorry, that this is a dependent system of equations? Let me go ahead and substitute again. I'm going to say here that y is negative x plus 2. I'm going to take this value for y, substitute it in for this y. 3x plus 3 times the opposite of x plus 2. Okay, what am I doing wrong here? 3 times the opposite of x plus 2 is equal to 2. And hear that buzzing? Somebody's calling me. So I'm going to ignore it. 3 times the opposite of x. You know what my problem is? Remember what I've told you over and over. Make sure that you have copied your equation properly. Incorrect right there. How could I have known that I had it incorrect? Well, I've been doing algebra for a long time. Let's see what happens here. We have 3x plus the opposite of 3x plus 6 is equal to 6. 3x's go away. We have 6 is equal to 6. If we have an obviously true statement, 6 is equal to 6, 2 is equal to 2, 9/10 is equal to 9/10, you have a pair of lines which are collinear. One lies right on top of the other. It is a consistent solution because it's a consistent system because there is a solution. It is a dependent system because there are an infinite number of solutions because the lines are collinear, which means that the lines are in fact the same. How do I know that? Look at this equation right here. Do you notice anything about the 3's and the 6? That's right. Common factor of 3. If you factor 3 out, you have x plus y, 3 times 2. Now if we divide both sides of the equation by 3, we end up with the exact equation as up there. Lines that are collinear have a multiplier that's been added to them. So it looks different just for a split second, but then you realize that you actually have the same line. Just divide this by 3. 3 divided by 3 is 1. 3 divided by 3 is 1. 6 divided by 3 is 2. And that is how you can tell that. Example number 1, we have a system of equations that we're going to solve for. And I went ahead and turned my page before I was ready to do that. So now I have to flip it back. The Adventures of Live Video Recording. I guess that's not video, hasn't been for a long time, but just in deference to my gray hair, I'll call it video recording. Example 1, page 285. Page 285, this says solve the system 2x plus 3y is equal to 16. Four x plus 5y is equal to 28. 4x plus 5y is equal to 28. See if I can make that just a little bit neater for you. 2x plus 3y is equal to 16. 4x plus 5y is equal to 28. There's nothing particularly nice about this right now, no easy variable to solve for. In the next section you'll see a trick that makes it a little bit nicer, but for now I'm just going to go ahead and solve for 2x in this first equation. I have 2x is equal to the opposite of 3y plus 16. Now I have to divide both sides of this equation by 2. And I end up with a particularly yucky looking mess of numbers and letters. Even though it's yucky looking, negative 3y plus 16 divided by 2, it's still a value for x that we're going to substitute into this second equation here. We have 4 times the quantity, the opposite of 3y, so that's 16 plus 16 divided by 2 plus 5y is equal to 28. Now fortunately there's not anything difficult about this. Remember 4 can be written as a fraction over 1, giving us a common factor of 2. So we now have 2 times the quantity, negative 3y plus 16 plus 5y is equal to 28. We're going to distribute the 2. 2 times the negative 3y, negative 6y, plus 2 times 16, plus 32. Plus 5y is equal to 28. Plus 5y is equal to 28. Negative y is equal to, combining several algebraic arithmetic steps here that you're allowed to do. Negative 6 plus 5 is negative y. Positive 32 minus 32 goes away. 28 minus 32, negative 4. Y is equal to 4. Okay? We now have a value for our y coordinate in the solution. I'm going to erase this mess. We have a value for y, which is 4. I will substitute that back into the first equation. 2x plus 3 times 4 is equal to 16. 2x plus 12 is equal to 16. 2x is equal to 4. X is equal to 2. I don't expect you to be able to write your things as rapidly as you can talk, but at this point in Algebra 1, you should be able to say, okay, 2x plus 3 times 4 is equal to 16. Okay, I'm going to have to multiply now. 2x plus 3 times 4 is 12 is 16. You should be thinking, oh, I just subtract 12 from 16. 2x is 4. I'm going to divide both sides by 2. I'm going to end up with x is equal to 2. If you're not at that point yet, that's okay. But practice until your brain has these patterns just ingrained into it. Like when water is rushing, it makes a path that it follows. You will get to where you can almost do algebra automatically in your sleep. We now have x is equal to 2, giving us the ordered pair 2, 4 for our solution. Let's see if this works. Does this work? What happens? If x is 2, I have 4, plus 3 times 4 is 12. Yeah, that's equal to 16. Check this. 4 times 2 is 8, plus 5 times 4 is 20. Yeah, that's equal to 28. You don't have to go through a formal step-by-step check here, but you're wise to look at your answer and make sure that, number one, it makes sense, number two, that it works out. So what sort of an equation, what sort of a system of equations do we have here? It has a solution, which means that it is consistent. Now, does it have one solution or does it have an infinite number of solutions? Well, it has a single ordered pair that tells us we have intersecting lines, so this is an independent, just like an independent contractor works on his own. An independent system of equations has one and only one solution. So we have been working with linear equations so far as we've been working with these simultaneous equations, which means that they all have first degree variables. We have an x and we have a y. We don't have an x squared, which would be a non-linear system of equations. Let's go ahead and look at this. Example 2 in your text. And you might be tempted to think, oh no, I can't do this, Miss Weibel. You're so mean, you're so mean. Well, no, it's very straightforward. Solve the system. X squared is equal to y. X squared plus 3y is equal to 64. All we are doing here is realizing that we've already been given a value for y, haven't we? It's written reversed, but it doesn't matter if you have something that's equal. It doesn't matter if you read it left to right or right to left. So y is equal to x squared. We have this value of x squared that we can substitute in here. X squared plus 3 times x, what did I do wrong? X squared plus 3y, isn't that what I said just a minute ago? X squared plus 3 times x squared is equal to 64. What is 3 times x squared? 3x squared. X squared plus 3x squared? 4x squared is equal to 64. Divide both sides of this equation by 4. X squared is equal to 16. Now what do? To remember, you go back and you take the square root. The square root of x squared is equal to plus or minus the square root of 16. X is equal to plus or minus 4. How does plus or minus 4 fit into an ordered pair? It doesn't, does it? But a plus 4, as I write a 2, a plus 4 fits into one ordered pair. A minus 4 is the x-coordinate of a second ordered pair. Okay? Y is equal to x squared. This is actually the graph of a parabola. Now, let's see what we get if we substitute a 4 or a negative 4 in for y. Let's go ahead and erase this. What happens if we put a 4 in? 4 squared is equal to y. Y is equal to 16. What happens if we put negative 4 squared in? Well, you have negative 4 times negative 4, which is 16. So your y value is the same. You have two possible ordered pairs. Okay? Let me review this again for time number 92, probably. The opposite of 4 squared is 16. The opposite of 4 squared is a negative 16. This says use negative 4 as a factor twice. Negative 4 times negative 4 is a positive 16. This, however, says take the opposite of 4 squared. In other words, use 4 as a factor twice and then take its opposite to get a negative. This right here is an excellent example of why, when someone asked me in class on Friday, why do we go ahead and put the substitution inside parentheses? It's to make it really clear what you're supposed to be doing, because without these parentheses, you might or might not get the right answer. That's the end of section 7.4, and I will see you next time.